Okay, so we're going to cover sections 2.1 to 2.3 in the geometry book, and it's kind of giving a brief introduction to proofs. We're starting out with inductive reasoning, which is basically when you're observing data and finding patterns in that data and then making generalizations so that you can expand the pattern to other data. For example, if I gave you this pattern, you would pretty quickly notice that there's a pattern. Goes up by 4, goes up by 4, goes up by 4, goes up by 4. You're going to notice that pattern and say, well, if it keeps following that pattern, this one should go up by 4 also. Your next answer should be 27. And that's using inductive reasoning. Also, it can look like this if you have a pattern something like this. I think. From here, you added 3, added 4, 5, and 6, and by looking at that pattern, you can assume that here they're going to add 7. That's inductive reasoning. Also, in proofs, use deductive reasoning. And that's when you take proven fact and then use logic to prove that other things are fact. So you're proving that certain statements are fact by showing how they connect to proven fact. For example, if I was trying to create a conjecture about obtuse angles, so I have an obtuse angle, and I say if an obtuse angle is bisected, which is split equally in half, then the two newly formed congruent angles are blank. You have to fill that in. Well, what we already know is that an obtuse angle is between 90 and 180 degrees. And we know that bisected means split in half, so you know that this part will be exactly the same as this part. Right? So now we know that both of these have to be acute angles because it's less than 180 degrees and you're splitting it in two. So it can't possibly be more than 90 degrees. So that's the use of deductive reasoning in a very simple proof. Next we have an arithmetic sequence, which is pretty common in just simple algebra. So if I had a number set like this, and I wanted to know the 200th number, you might think it'd be tough to tell you, but it's actually really easy. You notice that each time you subtract 5. So you have negative 5 every time. So you know that your slope is going to be negative 5 because it goes down negative 5 by every n. N stands for number. This is the first one, second one, third one, fourth one. This is the first number in the pattern, second in the pattern, third in the pattern. So every time, for every n, you're going to subtract 5. And we know that this pattern here is n1 and 7. So we're going to say that this is n1 plus something equals 7. It's completely arithmetic. So you know 7 equals negative 5 plus b. b equals 12. So now you know that the slope of this line is negative 5. And you know the y-intercept is 12. So now you know the equation of this. So if I plug in 200 for n, I have y equals negative 5 times 200 plus 12. And that's negative 1,000 plus 12. Negative 988 is going to be the value of that. Arithmetic sequences are always linear functions. For example, why did I just get rid of all those points? My bad. So these are the same numbers that we just had. Here's the n value for each one, for the first number, second number, third number, and this is the value that each number had. So I'm going to plot these on a coordinate graph. So 1, 7, It's going to be a very rough graph, but should be okay. Like that. It's just a very rough sketch of it. If you connect them all, well, if you connect them right, you'll see that it's a straight line. So it's a linear function. Arithmetic sequences are always linear functions, and that's pretty obvious because you can tell what the slope is. And that covers through section 2.3.